This is Lesson 1, How a Turbine Works. In this and following lessons, you will learn about the basic principles which make turbine engine a highly reliable power producer. Understanding how the engine works in most basic terms will allow you to build your knowledge of these complex processes more quickly and thoroughly. This lesson addresses these processes at a fundamental level and provides the foundation for the remainder of the course. When you finish this lesson, demonstrate your understanding by taking a progress check on the following performance objectives. 1. List the 4 processes of engine operation. 2. Identify the location of energy conversion into useful power. 3. Name the 2 ways expanded gas is used by the turbine rotor. Your instructor is John Lovejoy.
The industrial turbine engine is an internal combustion engine which produces horsepower by using the energy of highly compressed air mixed with fuel and ignited under special conditions. It is in the ignition and combustion process that heat energy is produced, which is converted into power useful for work. Continuous operation of the engine requires that 4 processes occur. Compression, atmospheric air is compressed. Combustion, fuel is added to the compressed air and ignited. Expansion, air and combustion gases expand through nozzles. Exhaust, air and combustion gases are discharged into the atmosphere. To begin the process of energy production, air is first drawn into the compressor, where rows of blades compress the air into an increasingly smaller space. Energy to turn the compressor is first supplied from the external start system until the turbine has enough power to turn the compressor over by itself. After the air leaves the compressor, it enters the diffuser area. In the diffuser, an additional pressure rise occurs. The pressure at the exit of the diffuser is about 118 pounds per square inch at operational speed and full load, right about here. After the air leaves the diffuser, it enters the combustion chamber, where either liquid or gas fuel is added to the air. This highly pressurized air and fuel mixture is then ignited by a fuel-fed torch. The combustion process releases the energy of the fuel in a temperature rise in the combustor, and after ignition has taken place, the hot gas expands very rapidly so that its velocity and its volume increases. The average temperature in the combustion chamber is about 1600 degrees Fahrenheit. These hot gases expand through the turbine section, deflect the turbine rotor blades, and turn the turbine rotor. The turbine rotor then produces the power to turn the compressor and produces the power to turn the electrical generator. As the expanding gases flow through the turbine section, their temperature and pressure drops, and they ultimately exit the turbine into the atmosphere through the exhaust diffuser.
Now that you've seen the basics of how a turbine engine works, review what you've learned. 4 processes which permit the engine to operate are compression, combustion, expansion, exhaust. Energy converted to useful power at the turbine rotor. The turbine rotor provides power to drive the compressor for sustained operation, the generator for electrical production. You have seen how compressed air and fuel are combusted and how this rapidly expanding hot gas is used to turn the turbine rotor. Smooth operation is achieved by transferring some of this power in further compression of air. The turbine engine is a heat engine converting heat energy into power. Each of the four processes contribute to the uniform performance of the engine, and we examined in more detail in the remaining lessons of this module. You have completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check now. This is lesson 2, understanding air. This lesson is about air. Air is the most critical requirement of the turbine engine. The way air behaves explains how the engine is able to produce power. In this lesson, you will learn some interesting and important facts about air. These facts explain why the turbine engine can use air to great advantage through energy conversion. At the end of this lesson, you may demonstrate your understanding by taking a progress check on the following performance objectives. 1. Explain the terms temperature and pressure. 2. Describe the relationship between pressure and temperature. 3. Describe the effect of compression on pressure. 4. Describe the relationship between pressure and velocity. Now here is your instructor, Don Lovejoy.
The turbine engine uses heat and pressurized air to perform work. There are several properties of air which should be kept in mind in order to understand how air and heat are put to work. These properties explain how energy is converted from one form to another. The turbine engine is designed to take maximum advantage of energy conversion. We know that air consists of minute particles invisible to the eye called molecules. Molecules are in constant motion, colliding with other molecules and with the walls of any container which hold them. Temperature is simply a measure of the speed of molecular motion. When air molecules are moving slowly, we measure a low temperature. But when molecules are in rapid motion, the temperature reads high. When molecules are enclosed in a container, some of the molecules will strike the walls at all times. The faster they travel, the more force they strike the wall with. This force is measured as pressure. Since temperature is a measure of molecular motion, if we add heat to a container of air, the molecules move faster. Heat energy is transferred to energy of motion. But when air molecules move faster, they exert greater pressure. So temperature and pressure are closely related. In fact, for each increase in temperature, there is a corresponding increase in pressure. Another property of air which is important to turbine operation is compressibility. If we attach a pump to our container, we can add more air molecules to those already there. If we continue to pump air into the container, we would see the pressure rise. It's easy to see why. More molecules, the number striking the wall at any single moment increases. Since each molecule exerts force on the wall when it collides, it makes sense that pressure will increase when more molecules are pumped into our container. So energy has been converted into pressure through compression. Now there's one final but extremely important property of air. In order to understand it, we'll have to take the air out of the container and put it in a pipe. Let's add a reliable, steady air supply which will deliver a constant flow rate to the pipe. Remember that air flows through the turbine engine in a similar fashion. The air has temperature, pressure, and a forward velocity provided by our steady air supply. Now observe the result of constricting the pipe to half its diameter. Since the constriction must move the same amount of air as a larger pipe section, air must move through the reduced pipe faster. Failure to increase velocity in the narrow pipe results in blockage and reduced flow. But we see the velocity does increase. Energy is required to increase air velocity, and the energy required here comes from the existing air pressure. As energy is converted from pressure to velocity, we see the air pressure drop. When air flows to a constricted flow path, we observe a velocity increase and a pressure drop. If we allow the air to flow back into a pipe of the original size, the flow is now handled at a lower velocity. Since the velocity of air decreases, excess energy is converted into pressure increase. When air flows into a large pathway, velocity decreases and pressure rises. In the turbine engine, the unique relationship between pressure and velocity explains many operating principles. In the compressor, the air is slowed and compressed. In the combustor, the air is heated and expanded. In the turbine, the air is speeded up to be used to turn the turbine wheels, and then is exhausted into the atmosphere.
Let's take this opportunity to review what you've learned. Temperature is a measure of the motion of air molecules. Pressure is a measure of the force of air on a surface. Temperature and pressure are directly related. An increase in temperature results in an increase in pressure. Compressing air causes pressure to increase. Pressure and velocity are inversely related. As pressure goes up, velocity goes down. And when pressure goes down, velocity rises. Air is used to convert energy from one form to another. You know that heat can be added to air to increase the pressure. Likewise, by adding energy through compression, the pressure will increase. By altering the air flow path, energy of velocity can be converted to pressure energy. In each case, air is used to convert and transfer energy. What you now know about air can be applied directly to the turbine engine. In the next lesson, you will learn how the engine is designed to use these facts about air, put air to work. You have completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape, take the progress check now. This is Lesson 3, Principles of Compression. In this lesson, you'll learn about the compressor and how compression is achieved. You will see how the compressor is designed and study the effects of compression on air. Your understanding of these concepts will help you in dealing with routine troubleshooting and maintenance related to the air system and engine start sequence. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Describe the basic features of the compressor. 2. Explain what happens to air velocity, pressure, volume, and temperature in the compressor. 3. Explain the term diffusion. 4. Describe ways the compressor maintains air velocity. 5. Explain the term ECD and identify where it is measured. Here is your instructor, Don Lovejoy.
The principles of compression are best understood by first looking at construction of the compressor. Flow path is formed by an annular passage around the rotor assembly. As the air flows along the length of the compressor, the air path decreases in size. Since the path for the air is parallel to the rotor axis, the compressor is an axial flow type. The work of compression is done by several rows of blades, similar to the blades of an electric fan. Looking closely at these blades, we see that some blades are in stationary rows attached to the case. These are called stators. Other blades are in rows attached to the rotor assembly. When the rotor assembly rotates, these blades move much like a fan. These blades are the rotors. Small amounts of compression occur between each set of rotors and stators. Each pair of rotors and stators is a stage, and this compressor has 11 stages. At each stage, the rotors speed the air up and the stators slow it down. In slowing the air's velocity, the energy from velocity is transformed into a slight increase in pressure. While the velocity of air remains almost steady, the pressure is increasing as it passes through each stage. Each stage multiplies the pressure obtained from the preceding stage. A very small pressure in the first stages quickly becomes a very high pressure by the last stage. Remember that the air path decreases in size along the compressor's length. This permits the compressor stages to maintain the pressure passed along from the previous stage. Now, with an increase in pressure goes a similar increase in temperature. So the air leaving the compressor has gained high pressure and a high temperature. This is done by alternately speeding up and slowing down the air in an ever-decreasing volume of air path. The question you may be asking yourself is, how does air movement get changed into pressure? The answer is related to the shape of each compressor blade. Each blade is shaped like an airplane wing or airfoil. In the airfoil, air flowing over the top must travel over a longer path in the same time as the air on the bottom. To do this, the top airflow must increase its velocity. You recall that when velocity increases, pressure drops. This is how a low pressure above the foil and higher pressure below is obtained. This difference in pressure creates a lifting force that pushes the airfoil towards the low pressure area. Now let's look at the compressor blades again. At the first stage rotor, a low pressure area is created on this curved surface as the rotor rotates. Air from the atmosphere then rushes in to fill this spot. The rotor blade motion increases the air velocity and moves the air into the spaces between the next set of stator blades. Now, whenever air is forced through an enlarging air path, the velocity decreases while the pressure rises. It's at this point, in the space between stator blades, where air is slowed down and we gain air pressure. This is called diffusion, and it is the key principle which makes the compressor work. The space between rotor blades acts as a diffuser too, slowing the air velocity. Won't the air eventually stop if we keep slowing it down? No, it won't stop because two things are occurring which maintain air velocity. First, the moving rotor blades add energy to the air and force it along to the adjacent stators. You remember that the air path along the compressor's length is decreasing in volume. Let's look very closely at the space between one set of rotors and stators. Here, the shape of the air path is decreasing. In fact, we have a miniature nozzle. This causes the velocity to rise slightly before the air enters the next set of blades. So the nozzle effect is the second way that air velocity is maintained. As the air moves between hundreds of blades on 11 stages, its pressure is multiplied by diffusion and its velocity rises and falls in the process. After leaving the compressor, another pressure rise occurs before the air reaches the combustor. The pathway the air follows is shaped like a diffuser. the diffusion path increases in area and the air velocity slows down so combustion can occur. It is in this diffusion pathway that the final pressure increase occurs. This diffuser pathway is formed by the diffuser case, the compressor bearing support housing, and the turbine bearing support housing. At the rear of the diffuser, air pressure is the highest in the engine. Since this pressure is most important in monitoring engine performance, it's given a special name, compressor discharge pressure, or abbreviated in engineering terms, PCD. PCD is measured at the turbine bearing support housing and is an important display on the engine gauge panel.
Here's a brief review of what you've learned. The basic features of the compressor include rotors, rows of moving blades, stators, rows of stationary blades, air path, decreasing size forward to aft, axial flow, air flow parallel to the compressor rotor axis. In the compressor, air velocity remains constant. Air pressure increases. Air volume decreases. Air temperature increases. Diffusion is the principle of increasing air pressure by forcing air through an expanding pathway. Air velocity is maintained by energy from moving rotor blades, nozzle effect between rotors and stators. The term PCD refers to compressor discharge pressure. It is measured at the aft end of the diffuser, in turbine bearing support housing. The compression of the air plays an important role in producing power. The design of the compressor permits large quantities of air to be compressed into an exceedingly small volume, both to sustain and cool combustion. Diffusion, the key to compression, occurs throughout the compressor. The result is the delivery of high-pressure air to the combustor without any significant loss in airflow velocity. Your knowledge of this material will aid you in developing skills, especially related to the air system and the engine start sequence. You have completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check now. This is lesson 4, compressor stall. Before moving on to other engine sections, the compressor operation must be explained further. In the previous lesson, you learned how the compressor functioned at normal operating speeds. At lower speeds, however, the process of compression is not nearly so perfect. If not carefully controlled, it can result in failure of the compressor to pressurize air. This condition is called stall. This lesson will investigate the causes of stall and how it is prevented. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Explain the term stall. 2. Describe how stall is prevented. To introduce this lesson, here is your instructor, Don Lovejoy.
In the previous lesson, you saw how the compressor was able to compress air while maintaining a constant airflow velocity. When the engine is running at normal operating speed, the stages are matched perfectly to accept the compressed air multiply the pressure by a small amount, then pass the air to the next stage. But at low speeds, the stages are not matched. The forward stages produce more airflow than the rear stages can handle. The rear stages become temporarily blocked, unable to move the large volume of air out of the compressor. The flow velocity drops, causing a stall condition. Let's use the airfoil to explain low-speed stall. The airfoil is designed to affect airflow to form a pressure differential across the foil which creates lift. There are three factors which affect the performance of the airfoil: its velocity, its shape, and the angle the foil meets the air. If the angle the foil meets the air becomes too great, the low pressure area begins to draw air back down onto the foil. This turbulent air condition upsets the smooth flow of air and destroys the low pressure area, which causes a loss of lift. When this happens, stall has occurred. In an airplane, stall makes the airfoil inefficient and lift is lost. When stall occurs throughout the compressor, airflow ceases. This condition is known as surge. When airflow decreases in the turbine engine, the combustor and turbine sections heat up rapidly to extremely dangerous levels. This will severely affect turbine components and decrease the engine's lifetime. Remember that stall occurs at lower speeds, where the forward stages are more efficient than the rear stages, and air piles up in the rear stages. Since each rotor blade is an airfoil, stall occurs on each rotor blade. Let's look what happens to the angle of air meeting foil as the air velocity drops. Using vector diagrams, here's the direction speed of the forward stage rotor blade. We'll call this vector A. And here is the incoming air. Vector B shows its direction and speed. The resulting angle of air meeting the rotor is vector C. This, of course, is the ideal situation, where air meets the blade at the angle the blade is designed for. But while the forward stages are pushing air to the rear stages aren't able to move it on rapidly. Here's the result. Vector A is now the direction and speed of the rotor blade. But the airflow has slowed down due to blockage in the rear stages. Here's vector B again, with its velocity component shorter than before, representing a drop in airflow speed. Here's the resulting relative speed and direction of airflow on the blades. Vector C meets the airfoil at an increased angle because air velocity has been reduced to half. If the rear stages continue to choke and the air velocity drops very low, it's easy to see what happens. Though the blades continue to rotate at the same speed, the airflow almost stops. Here, vector B represents very low air velocity. The relative angle of air meeting foil is so great that turbulence develops. And that important low pressure area over the foil is destroyed. Earlier you saw how the forward stages are perfectly matched to the rear stages at normal operating speeds. It's at lower speeds that the forward stages outperform the rear stages and stall occurs. To prevent stall at low speeds, the compressor reduces the amount of air which enters the first three rotor stages. This is done by changing the direction of airflow meeting the forward stage rotors and stators. The first stage rotor has a speed and direction shown by vector A. The inlet guide vane can direct incoming air at a new angle. Vector B shows the new angle. Its length is unchanged from before because the velocity of incoming air remains high. You see both the relative angle and velocity of incoming air are reduced, shown here by resulting vector C. By controlling the angle at which air enters the first three stages, a stall condition is avoided during the start cycle. The inlet guide vanes, the first stage stators, the second stage stators, are movable. and change the angle of the air entering the first, second, and third stage rotor assemblies. At low speeds, this reduces the volume flow rate in the forward end of the compressor enough to allow the rear stage of the compressor to move the air without choking and causing a stall condition. The inlet guide vanes and stator assemblies are adjusted automatically with increasing speed during the start cycle to match the forward and rear end of the compressor at all times.
Here's a review of what you've learned. Stall is a low-speed compressor condition caused by forward stages producing too great an airflow, rear stages becoming blocked, flow velocity dropping. Airflow stops because air strikes the compressor blades at too great an angle, causing turbulence and reducing lift. Stall is prevented by the variable guide vane system, reducing volume flow rate at low engine speeds. As you have seen, compressor stall can be destructive to the engine. Though automatic systems are designed to assist the engine in preventing stall, it is important you understand the concept of stall, the way the engine compensates for this condition. Stall and related surge will be the focus of several future lessons dealing with operational and maintenance procedures. You have completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check now. This is Lesson 5, the combustor and turbine. Now we explore the basics of how the combustor and turbine sections operate. This lesson will take you into the engine's interior for a close look at the events of energy conversion. During these processes, you will observe the forced air converted to rotary power. You will also see how the engine handles unstable air conditions. At the end of this lesson, you may demonstrate your understanding by taking the progress check on the following performance objectives. 1. Describe the functions of primary and secondary air. 2. Explain the nozzle effect on the turbine function. 3. Explain impulse and reaction. 4. Describe the term surge. 5. Explain the function of bleed air valve. Here with this lesson is your instructor, John Lovejoy.
It is in the combustor and the turbine section of the engine where energy conversion occurs and power is produced. Let's take a look at how this is accomplished. The combustor has one primary function: to produce heat for the expansion of air. It does this by releasing chemical energy which is stored in the fuel. Ignition occurs when a spark is applied to this air-fuel mixture and burning begins. This is often called light-off. The total combustion process is divided into two steps. First, the burning of part of the air with fuel, and second, diluting the combustion products with the remaining air. It is in this second step that all the air becomes heated, causing rapid expansion, which is used to drive the turbine. To see how these steps occur, let's look at the combustor. It's constructed like two concentric pipes. Combustion occurs between inner and outer liners. One end of the combustor, the forward end, is covered, forming the dome, while the other end, the aft end, has shrouds which direct hot gases toward the turbine. Combustion takes place near the forward end. Combustion uses only about 1/4 of the air available at full speed. This primary air enters the combustor through many holes in the inner and outer liners. But most of the combustion air enters through air blast tubes located adjacent to each fuel injector boss on the outer liner. Here you can see how the blast tubes are associated with a fuel injector boss. The extreme temperature of the fireball requires some protection for the liners. Metal guides deflect some of the air to flow along the liner surface to form a cooling blanket, so flames can't touch the liner. As combustion nears completion, toward the aft end of the combustor, the remaining air enters. This is secondary air. Two important events occur here. Air cools the hot combustion gases before entering the turbine section, and the air is heated and rapidly expands. Without this cooling air, the combustor would be one big fireball at about 3,500 degrees Fahrenheit, and metals in the turbine section cannot tolerate such temperatures for long. Also, by using heat of combustion to rapidly expand the secondary air, a great increase in airflow occurs. Airflow that will directly turn the turbine to produce power. It is in the turbine section where power is finally produced. The expanded gases from the combustor turn the fan-like blades of the turbine, producing rotary power. The turbine has some features like the compressor. Rows of rotating blades, or rotors, are attached to a single shaft, while stationary blades are attached to the outer housing. The Centaur engine has 3 stages in the turbine, each consisting of a row of rotating blades and a row of stationary blades. Taking a close look at the stationary blades, you see they are not like stators in the compressor. The space between blades forms a nozzle, and the compressor space was more like a diffuser. Nozzle design is important to gain a high velocity discharge from the combustor. The nozzle causes a significant increase in velocity and drop in pressure by converting heat and pressure energy into velocity. This high velocity air is used in 2 ways in turning the rotor blades. The first is by impulse. Air is directed towards the blades, forcing them to turn away from the nozzle, turning the turbine shaft. The second is by reaction. High velocity air expands as it passes through the rotor blades, pushing the blades in an opposite direction, again turning the turbine shaft. The Centaur turbine uses air in both ways, impulse and reaction. An impulse of air striking the leading edge of the rotor blade and expanding air reacting against the blade's trailing edge. Both ways together maintain the evenness of the turbine's rotation at operating speeds. The expanding gases drop in temperature and pressure as they drive the turbine. The gases then exit through the turbine exhaust diffuser to atmosphere. Before leaving the turbine section, remember that the turbine is designed to handle the large volume of air produced by the compressor and combustion, but only at high speed, what we call normal operating speed. During the start cycle, as the engine accelerates, the air produced by the compressor and heated in the combustor must all pass through a rather small passage, the first stage turbine nozzle. At low speeds, the compressor is unable to build enough pressure to force all the discharge air through the turbine nozzle. At low speeds, the turbine is just able to power the compressor with the aid of the start system, and there is little power to remove excess air. If this is permitted to happen, a stall or surge condition will occur. Remember, the compressor stall was prevented by matching the forward and aft stages during acceleration. The variable guide vane system automatically adjusts for stall. But between compressor and turbine, another solution must be used. Until the turbine has reached nearly red speed, the excess air must be removed. This can be done by bypassing the turbine section. In doing this, we reduce the back pressure on the compressor and reduce the load on the turbine. Bleed air valve is used to direct about 10% of the air around the turbine section. Like the variable guide vanes, the bleed air valve is automatically controlled to open during the engine start cycle and close as normal operating speed is approached. Unstable air conditions occurring in the engine are generally called surge. So the anti-surge control during engine start rests with the variable guide vane system and the bleed air valve.
Let's review what you've seen. Primary air enters forward combustor section, flows through air blast tubes, mixes with fuel and ignites. Secondary air enters the aft combustor section, cools the combustor gases, expands rapidly prior to entering the turbine. The turbine nozzles formed by the stationary blades increase air velocity and decrease air pressure. Impulse is the force of air striking the rotor blade. Reaction is the force of air escaping between the rotor blades, pushing the blades in opposite direction. Surge is any unstable air condition in the engine. The bleed air valve removes back pressure on the compressor and removes load on the turbine during startup. The processes occurring in the combustor and turbine release a large amount of energy which is converted to rotary power. Impulse and reaction forces are used in this conversion of hot expanding gases into rotation. With this lesson, you have gained a thorough understanding of the processes which contribute to the engine's operation. You now have the necessary knowledge to begin in-depth study of the turbine engine's operating characteristics. You have now completed this lesson. Now turn to your learning guide for review. If you wish to test your understanding, stop the tape and take the progress check now.